Before moving on, let us quickly recap what we were doing so that we don't lose track of what we are trying to do. Recall that what we want to do in these videos is to introduce the notion of definite integrals and then state the fundamental theorems of calculus. The fundamental theorems of calculus relate integration and differentiation. So to build up a feel for it, we need to understand the nature of integration and differentiation. Now, since calculus was physically motivated, the best way for us to understand these concepts is by looking at them through the canonical physical example of position versus velocity. Finding velocity from given position is the problem of differentiation, whereas finding position from velocity is, in a sense, the problem of integration. In the previous video, we started with the problem of finding velocity from position. We supposed that you went on a 6-hour run, run in quotation mark, along State Street. Since you're running in a single direction north, your position at any time t could be given by a single number, namely how far north you are. This defines a function s of your position with respect to time. So for example, if at 9 a.m. you are right here at 800 north on State Street, then we will write s of 9 is equal to 800. Now suppose that you have a very good GPS tracker. It gives you your exact position at every time during your run. We then ask whether from that data you could calculate your velocity. In the previous video, you objected that since your velocity changed, if I want to know your velocity, I have to specify over which time interval. And we agree to split your run into 3 equal time intervals of duration 2 hours each. In which case, you could easily tell me what your average velocity was on each of the interval. To figure that out for each interval, you just take the total distance traveled divided by the duration, the so-called change in y over change in x, or rise over run. In other words, we saw that your average velocity on a given interval exactly equals to the slope of certain line or line segment. In this drawing, your average velocity between 5 and 7 a.m. corresponds to the slope of this line, whereas your average velocity between 7 and 9 a.m. corresponds to the slope of this line, and that between 9 and 11 a.m. corresponds to the slope of this line. So you see that you started out running pretty slowly and then you speed up, and you were the fastest during the last 2-hour run. Alright, so that's how we would figure out your average velocity over some time interval, right? But is your objection valid? Is it true? But let us re-examine your objection for a moment. Is it true that we could only talk about velocity over some time interval? What if I want to ask about your velocity right now, right at this moment? That should be possible, right? Since we talk about that all the time. In your car, you have a speedometer that tells you your velocity at the current moment. So what does that even mean? Velocity is usually computed as the quotient of the change in position, i.e. the distance traveled, right, divided by the change in time, i.e. the duration of time passed. So what time duration would I use to compute the velocity at this specific instant? Say for example, how do I compute your velocity at 7 a.m.? If I had asked for your average velocity between 7 and 9 a.m., then you could have answered me easily. You would say, let's take the total distance you travel between 7 and 9 a.m. Let's note that by delta y, and let us just divide that by the duration travel, which is 2 hours. This would be your average velocity between 7 and 9 a.m. It's equally easy to find your average velocity between 7 and 8 a.m. You simply again take the total distance traveled and then divide it by the duration traveled, which in this case is an hour. You can do the same thing if I ask you for your average velocity between 7 and 7:30, and even for your average velocity between 7 and 7.0000001. To find the average velocity in all of these cases, you just take the total distance traveled and then divide that by the duration traveled, the amount of time passed, which I denote here by delta. But what is delta? When I want your instantaneous velocity at 7, your velocity right at 7. That sounds like the average velocity between 7 and 7, so then wouldn't delta be 0 in that case? And the total distance traveled would also be 0, so then the average velocity would be 0 over 0, which doesn't mean anything. That doesn't sound quite right, does it? So how do we rescue this and capture our usual daily intuition that there is indeed some meaning to saying that my current velocity is something? Recall that in class we mentioned 2 ways to formalize that intuition into a formal definition. One is via infinitesimal calculus, and the other is via limit. Since we have talked about this extensively in class before, now we're only gonna review the aspects that we need for discussing integration. Let us start with the standard approach, the limit approach. As we have said, to find your average velocity over some time interval delta, starting from 7, we just divide the total distance traveled over the amount of time passed. Now, if we denote the amount of time passed by delta, then the distance traveled can be computed in the following way. Just subtract your position at 7 a.m. from your position delta hours after, so that should be your position at 7 plus delta a.m. If you take that distance traveled and then you divide that by the duration traveled delta to get your average velocity during this time interval delta. To get your instantaneous velocity at 7 then, you would just take the limit of this average velocity as delta approaches 0, i.e. as the time duration becomes arbitrarily small. Graphically, because this average velocity between 7 and 7 plus delta is just the slope of this secant line, this limit here is just the limit of the slopes of the secant line as delta get closer and closer to 0, and so this limit is really just the slope of the tangent line at 7, which is the derivative of s at 7. Now, a more intuitive but less standard approach is the infinitesimal approach. This was the original way that Leibniz and Newton think about calculus, and was later revived and given a rigorous foundation in non-standard analysis. Here the idea is to actually take this time duration delta to be an infinitesimal number. Think of that as the duration of a moment, or say the size of a point. A positive infinitesimal number is any number that is bigger than 0 but smaller than all positive numbers. Again, just think about that intuitively, though not precisely, as the duration of a moment. Right? What's the duration of a moment? It cannot be any real number, yet it cannot be 0 either. So then with the terminology of infinitesimal, we can think of the instantaneous velocity at 7 as, roughly speaking, the average velocity during an infinitesimal time duration. To compute that, you would subtract your location at 7 from your location after an infinitesimal amount, so your location in the next moment, right? And then divide that by the duration of a moment. If your position function is so-called differentiable, then the result that you get is gonna round to a unique real number, which is your instantaneous velocity at 7. We have done sample computations with this in class, so we're gonna not repeat it here, but I just want to make a quick remark that in this terminology, we can now rephrase and redefine the tangent line at 7 as the secant line through the points with x-coordinate 7 and 7 plus an infinitesimal. Alright, so that's a quick review of how we would deduce velocity from position. If we have a position function s of t, then we can find the instantaneous velocity at any point in time, say 7, by computing the following quotient either as a limit or by thinking in terms of infinitesimal. Up next, we are gonna go in the other direction and finally get to talk about integration.